Okay, welcome back. It's a great pleasure to introduce our next speaker, Nachbin, who will tell us about water wave propagation on graphs. Oh, and he's from WPI.
Well, thank you very much, Ken. Thank you all for being here. It's really, needless to say, great pleasure, great honor to being at this important moment here of Carlos. And I would like, of course, thank the people who did really all the work in terms of organizing, and I'll thank everybody, but through Ricardo Leite, with whom I was in contact, but thanks everybody. So let me start talking a little bit about this work. This work of water waves propagation on graphs has to do with a thesis of a student of mine, Vanessa Simões. In 2015, we got a paper here at IMPA. So 2013-15, she was working on this problem. We got a very nice paper at JFM. It was there. It was a problem in my mind. I'll show you some papers that inspired me. It was in my mind for a while. And then 2022, I said, I got to go back to this problem. It's like it's itching back of my mind. And I was at the Newton Institute, a very distinguished audience. We have many distinguished people here too, like Sir Michael Berry and others. And I started my talk with the question I start now. Please let me know what I don't know, because I find the literature of water waves, particularly dispersive PDEs, on a graph very scarce. There's very little things. And I'll tell you about this, what we've been doing in this regard. And then in 2022, this audience, nobody told me like, oh, in 1967, this, that. No. So that's very good news in terms of this very nice playground for things I like to do, which is math modeling, theory of PDEs, as you will see, space for analysis and so on, scientific computing. And then over these 2 years I've been in the US, I've been giving many seminars and starting with the same question, and I've been getting some feedback. And recently, last year, I got some feedback and said, oh, look at the work of this person, that person. And I realized that this subject connects with something called quantum graphs. So, beginning of this summer, I started studying some quantum graphs, and I'll show you in this talk how these things connect. So please let me know what I don't know. And I think with Vanessa, we got a little bit of what I think sometimes is good, the benefit of ignorance. So the benefit of ignorance is then you jump into a problem not knowing what's out there, and sometimes you get ahead of the pack. As I'll show you some things we've been doing, is a little bit ahead of the pack of what's being done in quantum graphs. So that's the benefit of ignorance, right? You go, jump into a problem, you're not scared, and you say, well, let me try to do this, let me compare with that, and off you go. So this is basically the problem. So here's the setup of the problem. Waves. So I started actually with Vanessa. Let's do solitary waves on an open channel. So you have a 2D open channel. This is just so it looks more like a channel. It's just 2D open channel. And it's a forked region. Let's start with something simple. You have a solitary wave, gets into a region where it forks. And there's a lot of very interesting questions. And one thing we realized by comparing the 2D with 1D is that actually over in this region, away from the forked region, this is basically a plane wave. So it's basically the dynamics pretty much 1D. So we knew, I'll show you how in just a second, how to reduce the 2D Boussinesq weakly nonlinear, weakly dispersive PDE to a graph. And then it becomes a very sort of interesting, sexy math problem without much literature. And one of the things that you need a compatibility condition here, and Vanessa actually generalized, without us knowing at first, a very well-established compatibility condition. That's the story I'm going to be telling you today, and how it comes together with quantum graphs, which I've just learned. I studied at the beginning of this summer, quantum graphs, and connections are being made, very interesting, and so on. Okay, so the idea then of the talk is let's study solitary waves on the 2D domain that forks and see how we can reduce it to 1D. Why do we want to reduce it to 1D? Number one, you have a more efficient system if you want to do applications. Number two, very important, particularly for this audience, there's full of mathematical questions. It's a beautiful, wonderful, I hope you agree, mathematical playground for all sorts of skills. Let's see if I succeed with this sort of advertisement. Okay, so let's go. Oh yes, it's Carlos' birthday, and I have to say something. On purpose, I didn't say at the beginning. I have to say something. This is the Carlos I met in 1994 at the Courant Institute when I arrived. And when I arrived at the Courant Institute, Ruth Shore, which was the secretary for graduate students, immediately introduced me to Lucinha. She said, oh, there's a Brazilian student here. And Lucinha had studied in the same high school as me, so kind of recognized each other and said, oh, you got to meet another Brazilian. And the same day, this is first day at the Courant Institute, second day, or first day, introduced to Carlos, which actually had the same piano teacher as my former wife. So, you know, all the entanglement was established, Dona Dulce, and Carlos would come to and I was coming from engineering. So with no proper math background for the Courant Institute, my first year was never studied so hard in my life. It was really brutal. And two gentlemen in this room played a remarkable role of helping me gain my balance and my trajectory in mathematics. Carlos, that would be visiting Percy from Yale, and every time he would hop into my office, so what's the problem of the day? Like he would start asking things, discussing math with me, helping me very much in preparation for the written exam. And then at one point also, because of my lack of my proper background in math, my first academic advisor was not so happy, and so Carlos mentioned to Percy, which was the, I think, head or coordinator of grad studies, and Percy very kindly stepped in and said, look, let me handle this until you find an advisor, so which was eventually George Papanicolaou. And so Percy and Carlos, you all should know, played a very, very important role some almost 40 years ago in helping my mathematical trajectory, which brings me here. So then I passed my written exam at the Courant Institute. I started working with George Papanicolaou for my oral exam. I passed my oral exam. At the time, I never studied so hard in my life to catch up. And then when I passed the oral exam, you know, still working very hard. You work very hard, but it feels different. My mind a little more at ease, right? I went then back to a hobby I used to do here in Brazil, of which I was basically self-taught. A hobby, very cheap hobby. New York is expensive, we all know, right? Sometimes Carlos would take me to movies, Film Forum, which I would end up taking a nap, some really abstract movies. He would take me there, but it was okay. So here is my hobby, which Carlos was an inspiration for my hobby. And here you see. So this is Carlos doing some total flow in Lower Manhattan, right? And this, you know, I used to do cartoons here in Brazil when I was in college. And, you know, this cartoon has a mathematical message, important mathematical message. Note, I mean, when you do applied math, you know that nature solves problems in a very efficient way, right? So you see it here in terms of looking for a diagonal matrix and so on. Carlos is not so happy, but if you're smart as Carlos, you very quickly go to higher dimensions. So that's already a good thing to know. And to finish this of like the good old Courant days, then my hobby, which was a cheap hobby when I had a little bit of time to relax. There was some also very inspiring people. So there's these caricatures I did at the time, cartoons. Here, Peter Lax balancing himself on a Cauchy problem, right? And Louis Nirenberg, great name in pseudo-differential operators, trying to get a connection here with a. And this professor, also very important in my first year at the Courant Institute, which was teaching real variables 1 and 2, measure theory, Monroe Donsker, who helped you also me very much in getting the background in analysis that I didn't have. And Donsker, I gave these drawings to the original people, and Donsker said, what am I doing here? What is this? And I said, Professor Donsker, your lectures was very animated. You would impersonate mathematical objects, and at the end of the real variables course, you would do an introduction to probability, and he would say, take a distribution function from -0 to 1. and then he would also say, take a Gaussian distribution, scale it by epsilon, and let epsilon goes to 0. It peaks into a delta function. So here it is doing this. And he said, he told me, do I do all this? I said, yes. And he said, oh my God, now I'm going to become self-conscious. I said, please continue doing it. Anyway, so I gave these originals to these people, and there's some more caricatures in my homepage. Okay, now I have to go back to science. So this is my little celebration of being with Carlos, meeting these two very important gentlemen in my mathematical training starting at 84. So basically 40 years ago. Time flies, right? I can remember vividly those days. Wonderful. Okay, so now back to this fun problem. So, okay, so I already presented this slide, so what do we know? So from the mathematical point of view, so this started like the equations and so on. It goes back to a paper by the equations to Theodore Wu from Caltech, 1981, where you start with Euler's equation. So not everybody here is a fluids person. You start with Euler's equation. It's incompressible in rotation, so you use potential theory. What boils down to, you have basically a potential, Laplace's equation in the domain. It has a free surface. That's the hard part. You have Neumann conditions on the boundary because it's impermeable. And this is where things get complicated. You have the free surface condition. Eta is the wave elevation. Phi is the velocity potential. So you take so it's a harmonic function. So you need to solve a harmonic function here with the free surface, where that's the complications, right? Proving well-posedness in the analysis of this, where it's like, it's a problem, you know, the first one I think was by David Lan, 2003, so it's something quite recent. But it's a problem known and done for a long, long time. So Wu basically used something which is classical. He does a depth averaging of this problem, and you can reduce this problem to just the free surface. So I'm going to abuse of notation. Phi is a velocity potential, is a harmonic function, and now this is a Boussinesq equation. It's not the same phi, or else this would be harmonic. It's not, but it's still a reduced velocity potential because the gradient gives you the velocity field on the surface of the channel, 2D, U and V. Okay? And it called my attention as I went along before working with Vanessa, these beautiful pictures by these people, Michel Tang, I think was a postdoc or a student of Wu, doing wave reflection on a branching channel. My thesis with George Papanikolaou was waves over random topography, so I was already used to wave reflection over depth variations, which basically from the PDE point of view means how does a wave interact with the variable coefficient in the weakly dispersive, weakly nonlinear PDE. My thesis was just first the linear part. So these are very nice figures showing how a solitary wave, plane wave, comes and reflects and does all these complicated things, but they could only do it also numerically, basically for these degrees of multiples of 45 because of the finite difference scheme, so the grid would fit and so on and do the computation in a good way. So this called my attention, and off we went into understanding this problem. And here's basically the conclusion, and I'm going to show you the story of the study with Vanessa. Vanessa from IMPA, Vanessa Simões, she did her thesis. We got this GFM paper, and we basically did a dispersive waves on graphs, where I said the literature is scarce. We did the reduction, systematic reduction from 2D to 1D. We get a 1D Boussinesq system. I'll show you this as we go along. And here's the thing that still stands. And I'm very kind of proud. This is where the benefit of ignorance. Nobody does this. Number one, nobody has on the graph any information of this angle. Quantum graph people don't have. And I've been recently in a meeting, a Banff research station meeting in Granada with some people from quantum graphs and talking like Dmitry Pilinovsky and so on. And, you know, I think I made it a case, like, we got to put angles. Some problems, it's not that important, particularly some problems which are flows on graphs. This is wave scattering on a graph, on a vertex. The angle is important, and I'll show you why. So nobody does this, and also nobody does, because it's very hard, and recently I got some reference to, the comparison between the 2D and the 1D model. We do it numerically. Analytically, it's not easy, and people in Granada told me one paper I'll show you later on from quantum graphs where people do the spectral analysis of these problems, and in particular this reduction. Okay, so some references of water waves models on graphs that were inspired. This is a paper that inspired me, that I knew for a long time, SciEM paper by Pablo Jakovskis, that actually I learned later on that's actually Esteban Tabac's former advisor in Argentina. And he was studying basically shallow water waves directly on the 1D problem. Forget about the 2D problem. And basically the analysis where he was doing some sort of, well-posedness for the linear problem understanding was basically it came down to a hyperbolic system. You know, this is a hyperbolic system, it's a shallow water equation, constant depth, a constant current, gravity. It's a hyperbolic system. He called this type 1, type 2. With Vanessa, we were doing actually type 2, a branching forked, but you can do either one. And then he had these conditions here that were called the Stoker conditions. And I knew this, Stoker, former professor at NYU. And this condition, what does it say? This is the condition here at the node. It says, it's very intuitive. It says that the wave height should be continuous at this point, ijk. And this is conservation of mass, where the b's are basically the widths of each reach before you sort of collapse it to 0. So kind of keeping the aspect ratio. Fine. So this is very intuitive. And actually, when I learned about quantum graphs, I learned that actually what I was calling the Stoker condition is well known in the quantum graphs community as the Neumann-Kirchhoff condition, where Kirchhoff comes from this continuity of, say, the current if it was, and Neumann is basically flux. And with this condition, Jakovsky shows that this system is okay. I mean, it's well posed. You have uniqueness and so on using this condition at the vertex. And that's a condition the quantum people use. And I'll come back to this again. They use because they can prove, and that's very important, the self-adjointness of operators on what Cushman, another author that I came to learn, and actually we exchanged messages, calls it, on this singular variety, which is the graph. So with this condition here. All right. So, yes.
No, the previous one.
Oh, sorry. This one? The plus minus depends on this guy or that guy. That's it, right? Sorry. And I'll come back to this. But thank you. And please, I get excited, start speaking fast. Stop me and ask questions. Thank you. Okay, then there's this other paper that I found later on. Jerry Bona came to Brazil. I discussed with him and so on, which is non-trivial. It's a BBM on the graph, and they're proving well-posedness. So they use it as an inspiration, this blood system, but then they look at the tree. They also use the Neumann-Kirchhoff for the Stoker condition. There's some problems with the model, and every time I say there's limitations or problems with the model, please do not take this as a criticism. Just take it as an alert. Because if the literature is scarce, you've got to start studying with what you have, right? And if it might be some model which has its limitations or this and that, that's not a problem, right? You're going to prove theorems when you can. So, but this model has a problem because it's a unidirectional model, and you're going to have reflections and so on. And they prove well-posedness on finite trees. So Boussinesq, this type of equations on the half-line or in intervals is not simple. But actually they mentioned, look, we have no information on angles, but it should play a role. And actually it does play a role. And they report some reflection transmission at the vertex with numerical simulations, which already tells us that, hey, instead of using a unidirectional model, you should have a bidirectional model, which is Boussinesq. Okay, here are papers that then I learned very recently. This is a very nice paper, which is a review paper by Alberto Bressan, Penn State, and collaborators, but it's basically on hyperbolic systems, basically on flows, not waves, and well-posed and so on. Only 1D, no angle, no comparison with 2D. Well, as I said, fine, very important, no rigorous mathematics, but it's flows and not waves, mostly flows and waves, and no angles. Then Dmitry Pilinovsky, who is the editor of Physica D and Studies in Applied Math, had this sort of review paper of standing waves on quantum graphs. So there's no propagation, and that's what I'm interested in, scattering, which is how does a wave propagate and reflect out of a vertex. And there's very recently, with Roy Goodman, that was also at Granada, he has actually a MATLAB package called Quantum Graphs Lab, where he's already putting some PDEs, Laplace equations. So a lot of the analysis, the spectral analysis on graphs, is based on the Laplacian and things of the like, in understanding eigenfunctions, eigenvalues, spectral analysis on this sort of not really 1D domain, right? So this, what Cushman calls it, this complex singular variety. Okay. And this is the book I bought recently by Berkoleko and Cushman, right? And actually Berkoleko has a very nice introductory paper that helped me a lot understanding things. And it's a book very much based on the spectral analysis, proving self-adjointness of operators in these complicated domains. And here's the definition that these authors give now of quantum graphs. It was inspired by a Schrodinger type equation on the graph, but now that's why I realized, wait, I may be doing some quantum graphs. Because quantum graphs is basically, you have a magic graph, a graph where you have the notion of distance between nodes, equipped with a differential equation, right? Which started like Schrodinger, Laplace, and so on. You put it whatever you want. You put a Boussinesq equation, you put whatever you want, and you start studying the dynamics on this funny-looking, interesting domain. Funny-looking, interesting domain. So this is a very important book. And here's a mention that they do is important, this is the terminology that Cushman used, important to have in mind, and I say it's not easy, it's not much done, comparison with the parent model, which is the fattened graph, which we did this green region. So this is the problem then we're interested in. This is what I sort of learned now in the beginning of the summer. So what is basically the spectral analysis, this in the most simple case, of course, there's very sophisticated case, spectral analysis on the graph. So they say, oh, start with it, the book starts like this, start with this Schrodinger type equation, forget about the potential, you're down with this Laplace eigenvalue problem on the graph, on this complicated, funny looking domain, which depending on the nodes, the topology, right, that's going to tell you something. And here are the Neumann-Kirchhoff conditions, the flux and continuity, and take this star graph, which is basically the type of fork region we're studying it, and do a Fourier analysis on this domain. So here's the Fourier analysis of lambda, which is the eigenvalue, it's positive, so you're going to put k squared, and you have, say for edge 1, you have these two modes centered, this one at the origin, which is the vertex v, this one centered at the end of the edge, and so on. So you plug these guys basically solve this equation, but they have to satisfy this traffic of information at the vertex. So you plug this into this condition, and you're going to get what's something that's interests me very much these days, the scattering matrix, which is the matrix associated with what comes in, what comes out of the node, of the vertex. Okay? So you do that, you plug this in, and then this guy sometimes works, yeah. And also, to my interest, that you can have the Neumann condition with a weight. These are called weights, which is basically would be for us the width of the channels that arrive at the vertex. But in the abstract case, it's just weights, even though not necessarily they add up to one. When you normalize it, they do. So now let's see how the scattering matrix is going to look like when you plug these modes into these conditions. You get this relation between so how these guys are coupled, they're coupled through this matrix, which is the scattering matrix, and this D matrix, which basically just has information about the phase difference because these lengths might be different. That's all. So this matrix is just a phase difference. This is the scattering matrix, and this is when you put the weights. Oh, and now they're going to look like weights because look, they add up to 1 and they divide by 1 over beta. So it is indeed like weights. And what is very interesting is that I'm going to go back at the end of the talk to the Jakovsky paper with the shallow water equations, and this matrix is going to appear in our wave problem. This submatrix here. So that's a scattering matrix, and it has to do how information that comes here hits here and goes away. Okay, there's a fly interested in the scattering matrix. Okay. So, all right. So this is basically one of the interesting things of this kind of problem. Trying to understand how is the traffic of information and how be solution properties as it bounces around. Come on. Okay, so here's a paper that I was told 2 months ago in Granada of, I don't know this person, he was not there, Olaf Post, but looks like a very good analyst in the topic with a lot of papers. And recently there's this paper where he's showing the convergence of spectra of graph-like thin manifolds. So the convergence of spectra from here to here, interesting enough, so that he can get, it's very sophisticated paper, he can get things and prove limits. He actually uses tubes rather than strips, right? My channel, I'm thinking of strips converging. He uses tubes. He has sort of a shaves, something that with Vanessa we did, sort of the corners. Of course, we get singularities from the corners. Got to be careful with that. So it has these sort of all rounded shapes, and it takes different, from what I recall from this paper I looked at very quickly, all sorts of limits. Limits are actually where the tubes of the edges converges faster than the tubes of the vertices and so on, and all sorts of spectral analysis properties of the eigenvalues and eigenfunctions as this guy shrinks, and how does it approach this guy, right? And one thing you want at the end of the story is that if you want to work with this guy, which I would like to work, you want it to be as best representative as it is of the parent model, right? You can prove things here, but maybe the things here are not that close to things on the parent model. So mathematically it's fine, it's an exercise, but from the application point of view of reduced modeling, you might have a singular limit in some sense, whatever. So it's very important, this type of analysis also, and scientific computing, checking things. Come on. Okay, so put them. Okay, so now let's go. Let me go to the work with Vanessa, which we actually did before learning many of these things, right? So I'm telling you a little bit like in the movies Carla would take me. Sometimes, the screenwriting is not in a linear way, right? You see things and come back. So how did we do this? The modeling, well, we started by using complex variables. Schwarz-Christoffel mapping came to play a wonderful role in this problem. So basically, to be able to deal with the angles and put the angles into the model, we use the Schwarz-Christoffel mapping, and you can think you can map this L shape. This is the canonical domain, the W plane, right? The mapping is actually in this way. And there's a wonderful toolbox, which I'll mention in a second, by Toby Driscoll. It's actually great to teach complex variables. There's beautiful pictures. So you can map, you have singularities here and here. Some points the Jacobian is 0. Some points the Jacobian blows up. If it's 0, it's non-conformal. And for branching channels, you're going to always map this canonical domain, and then the only price you have to pay is that you have this cut here, this branch cut of closing it, and you're going to, instead of having this complicated domain, as I'll show you next, you're going to have a Jacobian that keeps encoded information of the angle. So I'm taking angles from a geometrical point of view onto an algebraic coefficient, which makes our life quite easy. And then actually we can solve the problem in the canonical domain, and we don't have to worry about the grid if it fits the domain and so on. So we use basically Schwarz-Christoffel mapping. Yes?
Is it the interior? You're mapping the interior of those domains, right?
Yeah.
Another way you can think of it, so very good question, is the interior, yes. And another way of you can think of it is that I did this previously for potential theory problems, is that when you have, everybody does conformal mapping, usually thinking about Laplace equation because it's invariant, right, under conformal mapping, right? And then you think, okay, if I have Laplacian in a Cartesian coordinate, I have also Laplacian in this curvilinear orthogonal coordinate system. Here was the first time we decided, hey, why do I always have to do conformal mapping with the harmonic function? Here, I'm going to do conformal mapping just as a change of variables, and your question is good, and a boundary fitted coordinate system, because this is a level curve of the coordinate system in the canonical domain. So it's very useful in that regard, right? So we map this, and maybe regarding your question too, because we have singularities here and here, we map a domain slightly bigger, an epsilon bigger, even though this epsilon is not a proof, it's like intuitive, an epsilon bigger than the domain we need. I'm going to show you a picture later on. I think so. Okay, so let me do this here because it's faster. So this is what happens. Now my differential operator is not invariant under conformal mapping. Here's the original Wu equation. This is the one we use. Now we have a variable coefficient. And as you see in the next figure, it reminds me of the mountains I used to do in my thesis with Papanicolaou. Okay, so it reminds me of my mountains, a change of variables. So instead of you being x, y, now I'm c zeta. Okay, and we can do the 2D problem like this. Fine. And look at the Jacobian that actually the Schwarz-Christoffel toolbox prints out this beautiful picture. So it blows up here, it's 0 here, but it very quickly goes to a constant. So it's almost like a piecewise constant variable media. or topography, like steps. And that's what's going to generate the reflections as the wave passes by this region. So that's great. So here's the Jacobian already written using Cauchy-Riemann. Here is the equation. And this is how we're going to compute then this problem in the canonical domain, using a simplified domain, but with a variable coefficient. And then, since we realized in the computations with Vanessa that actually the wave is pretty much a plane wave once it's away from the forking region, right? It doesn't vary laterally. It's basically a plane wave. We said, hey, why do we have to solve then the 2D problem? Let's go to the 1D simplification. Well, the 1D simplification is basically saying nothing more sophisticated, just that the solution is zeta dependent. In the transversal direction, the solution effectively does not change. So therefore, you drop zeta derivatives, because it's going to be 0, and you get this 1D equation only in C, which is along the main axis of your channel. And that's basically then the equations we're going to put on the graph. It's going to be basically our quantum graph equation. It's going to be this equation, this Boussinesq equation, variable coefficient. Okay, the Jacobians here, variable coefficient. I differentiated the phi to get just the horizontal velocity. That's just a detail. And this is the equation we're going to solve on this domain. And then we're going to compare solutions here with solutions there. And we're going to realize that the well-established compatibility condition here is not that accurate, in particular when you have angles and so on. So, something still to be, as you'll see, we don't fully understand, and people don't use angles. So pay attention. Some problems, angle is important. So let's get to that. So here is the Stoker or Neumann-Kirchhoff continuity of the wave elevation, meaning here the wave elevation 1, 2, 3 has to be the same, and this is just conservation of mass. This is flux. Used to be the other notation, just that the flux 1 is equal to 2 plus 3. And that's the question was asked before, plus or minus. It depends on what kind of fork region you have. And then we do numerics with these models, and we realize that, hey, it didn't quite agree. So what are we doing here? This is a simulation of the Boussinesq system. Red is the wave here in this region, so this is red. Black is 2 is here, and 1 is the incoming wave. So this is a solitary wave incoming to the fork region, and there's nothing happening here or here. And then it's getting close to the vertex, okay, nothing here and here. And then it has passed by the vertex, here, passed by the vertex. So there's a wave here and a wave here, it means a wave here and here, and a wave coming back. And I'm comparing the dashed line is a 1D model with a solid line, which is the 2D model, and they're not matching very well. And actually, this is for a very, very narrow channel where they should be pretty much similar solution. And then when we use the improved compatibility condition, which I'll tell you how to get it, that Vanessa did, things improve quite a lot. So we get the solutions to match very well from the 1D reduced model with the 2D parent model. So what was done to improve this compatibility condition is what I'm about to show you next. And that's why comparing a 1D with a 2D model is so important, in which analytically it's very difficult, as I mentioned in the paper by Olaf Prost, which is doing a very simpler case, which is still very good, which is the Laplacian, those tube-like things, doing the spectral analysis there, proving it's very complicated. So what did we do? Well, and what caught our attention? Well, when you look at the simulations in the 2D case, so this is from Vanessa's thesis, you see a plane solitary wave coming this way. This is the asymmetric case, which, there's no such thing in the quantum graphs because they don't have angles. You cannot make a distinction between symmetric, asymmetric, and so on. So here's the asymmetric case, and look what's happening here in that region. The wave elevation in reach 2 is higher than the wave elevation in reach 3. And that's intuitive, because if you have the main reach here, there's going to be more water coming this way than that way. So that's natural. So asking continuity of the wave elevation is asking too much. And that's the Neumann-Kirchhoff established condition in quantum graphs, which in some problems it might be fine. In this problem for waves, maybe for flows it might be fine. For waves, not so much. So we were then saying, okay, so maybe how are we going to deal with this? The fact that this condition is not working, there's this sort of jump. And then Vanessa came out with a nice idea using from all this setup, and it goes like this. Basically, if you rewrite this equation here, which is the 1D equation, in conservation form, right? Just putting this guy, there's a t derivative here, pull it this side, here it is. You write it in conservation form, so it's like divergence form. Then, once you write it in divergence form, basically writing like this, you're ready to use a Rankine-Hurgonio sort of jump condition, shock condition. And because you know it's only here that the solution will sort of jump, you make a Rankine-Hurgonio jump condition with like a zero shock speed. It's always sitting there. So once you do that, right, and you basically have these two channels in parallel when you think of the conformal mapping. Because look, you have this separatrix in terms of coordinate system. You have these two guys, so you do a Rankine, we're going to go from 1 to 3, 1 to 2, and out comes this condition, which is a nonlinear Neumann-Kirchhoff condition, if we might call it, okay, from Vanessa, which is basically just saying that S plus is equal to S minus, because that means this is a stationary shock. And then, look, if I forget about this junk here, this nonlinear part, I'm saying that 1 is equal to 2 and 1 is equal to 3. That recovers the usual Kirchhoff condition. But now I have this nonlinear correction and excellent news. The Jacobian comes in, so the angle comes in an algebraic form in the vertex condition, in the flux of information. So, hey, that's good news, right? So, using this condition, the flux condition, the conservation of math, understand slowly and actually even stepping back, I'll mention to you in a second, to understand why, you know, it was good, but not so good. And, you know, what we understand is this wave scattering, in this case, just in a simple y, we can actually numerically add more vertices, but why do that if we don't understand the simpler case and further understand things? Okay, so examining, so this is something I did this summer, examining the Neumann-Kirchhoff condition and trying to understand it a little better. So then we step back and say, well, we don't, things are new, we don't understand this wave dynamics, wave scattering for these weakly nonlinear, weakly dispersive solitary waves, which are a beautiful thing that many of us here love, right? These very nice traveling waves. Well, then, you know, with two students that are here present, I mentioned Eduardo and Márcio and so on, said, I started in the summer looking, well, let me step back and just look to the linear hyperbolic system that Jacobi studied and see, you know, we understand the effect of angles, and let's understand how this would connect with quantum graphs. And it was great. It connects very nice with quantum graphs. And I'll show you. This is basically done in the summer. So let's go back to Jakovsky's equation, linear hyperbolic system. Take these three cases here, which the dynamics should be different, right? My intuition said, no way a wave comes down here and it's going to be the same, right? This a symmetric angle, asymmetric, very large angle. This is the downstream. This is upstream. Okay. Well, okay. How do we analyze this mathematically? Well, it's very simple, right? This is you can do it. Take this. You have this matrix, constant coefficient matrix. You can use the eigenvalues and the eigenvectors to change variables and write it as a decoupled system, which is this guy here, right? One eigenvalue which is negative upstream, an eigenvalue that's positive downstream. And the cool thing too is that when you decouple this, you have this, which I forgot to mention, you have this undirected graph that then becomes a directed graph. Basically, this edge here breaks into two edges in parallel, one that goes up and the other one that comes down. Then it's directed. And then you can ask the following simple question, which is, let me see information that comes into the vertex, to the node, and what comes out. Let's see the functional dependence of these guys, right? Okay, once we have it written like this, not difficult. So we go and we use the conditions here. I'm highlighting the red as the question. I was asked the red just because of this scheme, right? the condition before. And look, this is just basically the functional relation of what's incoming to the node. So incoming from the top or incoming from the bottom, right? Who knows, might be a wave also coming this way into the node, right? So this matrix, this relation, functional relation tells me incoming and outgoing. I want to know the outgoing, how does it depend on the incoming? And then the outgoing is the reflection. Okay, we can show, I mean, Jakovsky already argues that A is invertible, so that's why this system will have a unique solution. Well, if you invert A and you multiply by B, then you get the scattering matrix, which is, right, this guy here. And if you look at the scattering matrix, whoa, it looks exactly like that part of the other one that appears in quantum graphs, okay? And the good news, too, that I haven't done here, is that basically these right and left going modes, or down and upcoming modes, if I go to a nonlinear hyperbolic system, whatever, I can do the same thing because we have for this system Riemann invariants. And Riemann invariants are right and left propagating modes, up and down propagating modes. So maybe you can get that. We haven't done that. Understanding a little bit how to do for the scattering matrix for the nonlinear case and so on. So things to be done and understood. So this is basically then the scattering matrix for this problem, which resembles it's exactly the same as the one you see for the quantum guy, for the quantum guy. So there it was done Fourier analysis for the Laplacian and so on. Here it was done right and left going modes, up and down going modes, right, for a system. And of course, it's understandable because you do separation of variables here, you sort of can, get into the other problems. So it's not that mysterious either, the thing. And then there's another thing that's very important, which is this. If you then do something to show how the angle is important, let's do then a case which is actually called in quantum graphs a balanced graph. A balanced graph, for example, is a case where this incoming reach has width L, and the other two is L over 2, which means the total width of the channel is the same after you pass through the node. Okay? And then you find the scattering matrix for this case, and independent of the angle, this is the scattering matrix. And independent, of course, of anything, the fact that this guy is 0, it means that if I have this input, just a wave coming from above with this amplitude and time and nothing coming from below, nothing will go back above, will come up. So there's no reflection. And that means then that this system is limited. I mean, there's something in the modeling that's missing because look, it can't be the same for all these three cases. And if you think of a wave coming down for this T thing here, it's hard to imagine that nothing will refract in that direction. So that means, the Neumann-Kirchhoff condition for this model is missing something. How to restore it, how to put the angle back for this case, the linear case. Remember that the other one was a nonlinear Rankine-Ruggiero condition. So how do we restore this very simple model to do the right thing? It's not 100% clear yet, at least for me, and it's not done in quantum graphs because this is exactly the same scattering matrix as in quantum graphs, and actually most of the problems there are time independent. Sometimes they're time dependent. This one's time dependent. Anyway, so things to be asked and better resolved, which we find interesting. Okay, I think I have like, what, 10, 15 minutes? 10 minutes?
Yeah, you have 15 minutes.
15 minutes, yeah. Well, I stopped before. So here's a photo of a gentleman sitting back there with his mustache, Eduardo. And so Eduardo, he had two very nice animations that unfortunately I tried, and it didn't work in my laptop, of these two animations of this hyperbolic system in 2D, right? It's not on the graph, showing that actually when this wave comes in, it branches like this or branches like that. Here there's basically, it's a balanced graph. See, this is twice, so the widths add up to this. This one generates almost no reflection, but this one does generate a reflection. So unfortunately, we cannot see this on this graph. So we're playing with this, and Eduardo is, doing several simulations to solve different cases of this, and for this linear hyperbolic system in 2D before we go to 1D. And there's another gentleman sitting in the back, Marcio, who's doing his thesis too, which is basically trying to understand the error one has. I mean, the discrepancy, how things vary as you shave the corner, because you have a singularity here. So it's something we had already done in Boussinesq thesis. This is from pictures from Boussinesq thesis, which is a little bit you asking me, what do you map? So think of this, for this L-shaped domain, if you map a domain slightly bigger, which is this one here, okay, you get numerically a sort of a ringing when we did this, some sort of oscillations at the corner. And then if you use as your domain something just slightly smoother, but inside, which is this domain here, which is almost like a mollification of the singularity, the wave that sort of goes through the vertex or the corner, is pretty much the same, and the numerical ringing goes away. So that shows that actually this doesn't affect so much the main wave, the wavefront, but affects the dynamics. And what Basso is doing is, like, for example, this case of the L-shaped case is basically like a T branching thing, just the symmetry gives you this L-shaped part. This is a case actually he started studying too out of his initiative, which is, this is the only case when you have two corners that actually you don't get an elliptic integral out of the Schwarz-Christoffel transformation. You actually get it in closed form, the mapping, so you can play with it. And then Mas is trying to understand errors due to the sharp corners and so on, and playing with that, and also doing numerics and understanding things. So basically stepping back with simpler wave models, linear hyperbolic, but to understand things that are up in the air, fun and not looked at. So that's the idea. Let's say, okay, and I think I'm getting close to the lesson. And one thing for the future too, and since I like conformal mapping, and I want to mention this, and actually, one thing I should mention now too, going back to my oral written exam at the Courant Institute, right? It's linear algebra, complex variables, and advanced calculus. I remember Schwarz-Christoffel would rarely appear. And I remember we were studying, doing the old problems, and I remember Lucinha told me, don't waste your time with this, it only appeared twice. I said, okay, so I had so much to study, and in the last moment I said, okay, I have some time, let me take a look at Schwarz-Christoffel, and it came up in the written exam, and I think it was Harold Shapiro that did the exam. Anyway, so saved my life already in the writtens, and it's very useful for you. So now, look at this, just to finish. In this problem we used conformal mapping in 3D. It would sound a little bizarre, right? To use, I mean, complex variable is 2D. So how am I doing conformal mapping in 3D? Well, with a former student here at IMPA, Davi, I told him, look, this is a very interesting sort of topography, which is like the continental shelf, right? It's like ridges and non-smooth, right? Piecewise constant, non-smooth. And Schwarz-Christoffel is good for polygonal-shaped domains with corners and so on. So I told David, look, I mean, we still have potential theory now in 3D, but we have this guy here, which is a 1D topography. If you slice it, you can do the conformal mapping of a slice, okay? And then the Jacobian would be translation invariant. And the Laplacian will not be invariant, because the Jacobian is going to hit one of these derivatives and not wash off like here, right? It will hit. So can you get a Boussinesq system out of this? So in this science paper, David did this, and he got a Boussinesq system out of this case using conformal mapping in 3D. So this is the Jacobian, which is y independent, so it multiplies here and here, it's a variable coefficient. And at the end, at the time we weren't even thinking about this, but then we're doing something else. And then I looked back, and actually the Boussinesq equation that Davi got from a slightly different way is a generalization of the Boussinesq equation that Wu deduced and that we used for our channel. And that means now we can, that's something maybe for the future with somebody, do basically waves on graphs where actually the topography varies along every reach. So there's a composite reach in some extent. And why would that be interesting? Why would be that interesting? And I'll finish with this, because it goes back to a very interesting work I did with two French colleagues, Jean-Pierre Fouque and Jocelyn Garnier. Jocelyn, amazing doing things, which is, for example, this paper here. And actually, I did the numerics before we did the theory. With the theory, I convinced them to do the harder part, which is central limit theorems for random differential equations, which is this. Take this hyperbolic system, and here's the topography, and put a random coefficient there. Okay? The wonderful thing, and that's something that comes from learning from Papanicolaou and collaborators from the linear part of acoustic waves, and here's water waves, is that if you have a PDE, you have a wave, and you have a rapidly varying random coefficient on the right scale, like on an epsilon scale, it acts as a filter of high frequencies of your solution. So, in some cases, if you're in the right scaling, this filter of the solution, so you have the Fourier content of your initial data, this filter is a low-pass Gaussian filter. So if you have a low-pass Gaussian filter, in Fourier space, you have your initial data, Fourier content of initial, multiplied by a Gaussian. That's a convolution in physical space. Oh, but if I have a convolution with a Gaussian, the Gaussian is the solution of the heat equation. So I have a diffusion, the apparent diffusion effect. And that's what happens. So you have randomness on a pulse, a wave. We did it for a solitary wave and for a pulse. You have randomness. It acts as an apparent diffusion or an apparent viscosity. And here's the numerics. So if you don't have nothing, a shock starts forming. So this is just piling up the profiles. You see a shock start forming, some spurious oscillations from the numerics starts appearing. If you put the randomness, you get a viscous shock. So therefore, it's a very cool thing to say that you can regularize a solution with a stochastic or random forcing on a micro scale. And the thing is that every time the wave tries to break, right, it steepens, it produces high frequency. And the high frequencies are filtered out. So there's this fight, and it never breaks. So this is the apparent diffusion. And we did the same thing in another paper for solitary waves. And basically what this paper shows is that, for example, you use the Riemann invariant of the underlying hyperbolic system. This is not a hyperbolic system, but again, who cares? You borrow it. You get a Riemann invariant from the hyperbolic system. You abuse of terminology. Riemann invariant is such a beautiful thing. You cannot change the name. So you have a slowly varying Riemann invariant, right? It's a little weird to say that. Sometimes it's very slowly varying due to the dispersion. And actually, Jocelyn, after we did the model, and then Jocelyn pushes the limit theory and so on. And basically, then you get that the right-going mode, the right-going Riemann invariant of this Boussinesq system is a Burger's KdV equation. What does that mean? It's a KdV equation because this comes from a Boussinesq system, and Burger's because of the apparent diffusion filtering the solution, and we see that numerically as we see in these things. So that's basically something to be done in the future. I don't think that much of a near future because so much on this playground where you can have now like quantum-like graphs which composite edges, right? Heterogeneous edges, which actually if you have a shock forming, if you put randomness might help. Anyway, a bunch of things to be played with. So this is some of the references. And last, before I finish, Carlos, I have bought this for you. I mean, this bag says older, wiser, and weirder. Don't pay attention. It's the only bag I found. It's the only bag I found. Nobody. Don't pay attention to that. It says older, wiser, and weirder. No. Don't pay attention. Happy birthday. Thank you very much for your attention.
Thanks, André. Questions?
Let me bother you with the... So add a little bit of circumstantial to the water wave modeling. Does it change dramatically the way we interact with the corner?
With a what? Which interacts with what?
Add a little bit of circumstantial.
Yes, okay, there I go, yes.
Does it change dramatically the way the waves are going to interact with the corner?
With the board? With the corners? Good question. Good question. I would guess that The wave, the part that interests me the most, which is the wavefront, which actually for applications, say if it's a flood wave, you want to know how big is going to be the wave, it's going to reach certain city, whatever, blah, blah. So the wavefront, I think, is not going to change. But maybe these spurious wiggles behind, yes. I never thought of that, so maybe yes. If you put a little bit of surface tension, for example, could you not worry so much about shaving? I mean, you got to shave a little bit of the corners because you also have a Jacobian that's infinite inside. But yeah, maybe it might help. Yes, it makes sense at least. Okay, good question.
Percy.
Thank you for this very interesting talk.
Thank you, Percy.
Okay, so around, certainly in the US, there are many water wave labs. And so one could presume that people have done experiments with the splitting of the waves. There must be many experiments. Can one learn from these, or have people try to learn from these actual real experiments?
Well,
What is going wrong with the models that you have?
Yes, excellent question. So, excellent question. So, I just came back 3 weeks ago, a little bit, maybe this allergic sinus of mine has to do with so much traveling and so on. Just came back, it's 3 weeks ago from a meeting in Japan. And in Japan was Roberto Camassa, right, has a lab with Rich in North Carolina and so on. I was talking about this. And I said, I don't know of any experiments. Actually, Michelle Tang mentions about some very preliminary experiments on the T. But actually the results, she says she's not an experimentalist, first of all. So looking specifically at these issues of angle effects and so on, I think there are no experiments. There are definitely experiments in wave channels, as you said, in many places. In North Carolina, Rich and Roberto have a wonderful tank. And to corroborate with the fact that I'm saying there's not much experiments, Magda Carr from Newcastle, which is an excellent experimentalist and does a lot of experiments for Roberto and so on, for internal waves and so on, now in Japan, got very interested. She said she maybe would look into this problem. I hope she does, because as you said, that would be very enlightening for what goes on with the modeling and not. And one thing I mentioned to her that I think could be also another thing is that if you have these angles and so on, of course there's going to be some generations of vorticity, eddies and so on that changes also the effective width of the channel. So there's a lot to be learned, and you're correct. Lab experiments would tell what are the regimes where this kind of PDE is okay or it's not and so on. But I think in having Magda Carr get interested in it, she would know much better than me if it was already done or not. And I think there isn't much experiments.
Can you go back to the slide where you have a picture with 5 or 6, 5 or 3 that you do not understand this image? Yeah, first of all, what are you exactly plotting? Because you have 2D and 1D.
Sorry, Alessandro?
So you have a 2D model and 1D model, but what are you plotting?
So this is the wave elevation, right? So dotted is the 1D model, which is the model with the compatibility condition, testing the compatibility condition. And the 2D is basically the solid line, which is basically you do the 2D simulation, and it barely varies on the transversal direction, but then Vanessa would just average it in a very arithmetic, simple way, so that you get a profile, and then you compare both.
And numerically, what are you doing?
Numerically, I'm doing the finite difference method. Let me see if I have, at the end, there's something that would look like an answer sheet.
Because I was thinking that, it should be diffusive with the vector, right?
Sorry, no.
No?
Diffusive what, sorry? So here, I think here I have it. So look how I do it numerically. It's not diffusive, and actually we test first for a straight channel. The first test we do is straight channel, put a solitary wave, which is actually an approximation, high-order approximation to the Boussinesq system, because the solitary wave is actually an exact solitary wave for the Benny-Luke type thing, for the second order PDE, right? So the system to the second order, there's a little alpha exchange. So we put the solitary wave and we propagate it with the numerical method, and we see that there's no numerical diffusion, no numerical dispersion. It's a traveling wave, effectively speaking. And this is how we do it. And there's some actually fun things that we learn along the line, right now. So this is the equation. You bring this guy over here because there's this cross-regularized term from the Boussinesq equation. And basically what you do is you do finite difference over here on this side, you call this an auxiliary function, whatever, give it a name, f. So you solve this like predictor corrector, and then when you're done, you basically, since you evolved for f, you recover the phi by solving this auxiliary elliptic problem to recover the thing. That's what we do. It's basically this finite difference scheme centered, center second order, whatever. And when we did it for a straight channel, we saw a traveling wave, no diffusion, no numerical diffusion nor dispersion. We were happy, off we went.
Okay.
That answers your question?
Yeah, it's not a numerical issue then.
No, it's not a numerical issue. There could be issues, but, right? No.
Thank you.
Sure.
Next question, Charlie. Oh, sorry.
What kind of condition do you impose at the ends of the channels?
Kind of conditions? Just make it long enough so that no activity is there. So it would be like 0. Right? We have Neumann on the boundaries, the walls, which is boundaries and bottom. And at the very end, just like it starts 0 and it stays 0. We think of a Dirichlet 0, but we never run up to the point where the wave reaches that point.
So that these equations have finite propagation speed?
We have finite propagation speed, yes.
You never actually reach the end of the channel?
No, we never reach the end of the 7, yes.
You have to do these like Laplace solvers.
Which one? This one? So this is because the equation, remember that the equation, the Boussinesq equation, the dispersive term is like xxt, a little bit like the BBM equation, Benjamin Bona-Mahoney. Okay? So then you bring this t guy in here, you call this whole junk here f, so that this then looks like this ODE here, where if you discretize in space. Then you do a predictor corrector, so I advanced f, which means I advanced this guy. But I need phi again, because I'm going to have to compute this. So I have to then solve this elliptic type problem at each time step, so I can go from f back to phi.
So this is like the Yukawa equation, so it has exponential decay as you go out the end.
Well, the exponential decay is because of our initial data, which is post-shaped data, right? So it's already...
But even though it's phi plus Laplacian, so you're adding a positive term to a positive operator.
Yeah, oh yeah, that's true. Wait, that's true. Yeah, that's true. And and the phi is not going to. Okay, I forget now. Okay, how we put it at the end. Yeah, good question. Now I forget how, because the student, I forget how the phi goes to the end. Yes. Yeah. Sorry? Sorry?
The outgoing radiation condition is my particular obsession. So.
Your obsession, and we don't need a radiation condition.
I mean, it's not a problem for Yukawa, because Yukawa necessarily decays exponentially as you go out to infinity.
Yeah. Well, we just put a long enough channel, and we had no issues. Yeah, I forgot not the issues. Sorry?
What kind of bound condition that you do?
On the side is Neumann. So just Neumann, in a very simple way. Neumann just put the two guys equal to each other, right? For the wave and for the potential. But as Charles is asking me, which is a good question, at the ends, now it escapes me how it was done by the students. I forget now. But I mean, we have nothing there, right? We don't let the waves get there. But
So, sorry, we should probably wrap it up. Maybe there's time for one more short question. Who has a short question? Okay, it's okay. Two more short questions. Go ahead. You've been waiting.
and I'll try to give short answers too.
So, can you repeat, a similar story for flows in multi-component or multi-phase flows in porous media and replace porous media by graph?
I don't know, maybe.
Similar works?
No, there's a lot of work for flow, so instead of waves, so there might be things for flow in porous media. I don't quite sure, for example, in the Brest Sun, very nice review. There's a lot of cases about flows. There might be some mention about flow in porous media, but since it was not the thing I was paying attention, I would hesitate to give a definite answer if it's done, not done, but definitely it's a situation for that, yes.
We could discuss it.
So apologies to others who were still waiting to ask a question, but the last one goes to the closest to Carlos.
I want to make a comment.
Okay.
Priority.
Go ahead.
No, you do. I do. So, André, you're very modest. You say that you have the advantage of ignorance, at least in the beginning. I don't have any advantage because it's total ignorance. So, But my question is the following. As I understood, who made this simplification from 3 to 2?
Yes.
Okay. In 2, you forced conformal mappings because it's your business.
Okay.
Is there any advantage to take a little bit of that 3 piece and work instead of conformal, quasi-conformal? Because as I understood talking to Carlos, you get the angles both in the transformation, which like Christoffel, but you pay the price with the J. I just
The J with the singularity of the Jacobian.
Yeah,
Yes.
but if you work perhaps with quasi-conformal, which is being developed now by many people, do you think it's helpful?
I don't know. To be seen. I don't know. Yeah, because I mean, the way we get around is like mapping something slightly bigger, which is kind of shaving the corners, right? So, I don't know. I mean, it's a question, something to be investigated. Where is there an advantage? I don't know. I don't know. No, thank you. Yeah, I know.
Carlos.
I'd actually like to comment on your amazing lecture. I was reminded that when I've been through Darcy Thompson's spectacular book, right, about how blood vessels split in chunks, right? And their angles are absolutely fundamental, right? It's sort of the opposite problem, right? You're building up the graph, and somehow the physics imposes special choices of angles, right? I was just wondering.
Yeah, and actually at one point I looked at the literature of blood flow and like Quartapelli and so on. Some people in Italy had a lot of beautiful things and so, but when they do the reduction and so on, I didn't see much of that thing. Anyway, but again, it's flows, so there's another thing to really make sure too. Is there? I think there is a distinction between waves and flows. For waves, it's more dramatic, the angle and so on, right? So as we learn, to be seen, right? Even for flows, I don't know. Well, thanks everybody for all the very good questions and enlightening questions. So thank you.
Okay, thank you, André.
Thank you.
We should reconvene at 1:30.
So